capacitor. Simply, it's a component, okay? A component stores energy, okay? This is called capacitor. It's each plate stored charge, okay? We cannot say it stores charge because the resultant charge becomes zero. We'll be discussing about it, okay? And it has got many other functions, but the first basic thing is it stores energy, okay? And this energy can be used later on. Energy is stored definitely in the form of electric potential energy. Okay, it has other uses as well that we'll be discussing once we discuss its functions. Okay, G, so let's talk about its charging of its each plate. Okay, so see, for example, let's first discuss its symbol. Its electrical symbol is like this, two parallel equal lines. Okay, this is also called parallel plate capacitor. Okay, this is the symbol. Okay, if we discuss the symbol in detail, so remember these two plates are parallel metal plates. Metal plates that are parallel to each other, and there is an insulator between these two plates. Okay, insulator in our syllabus, it is only air, means free space. But this could be any other insulator as well. Another insulator can be placed between the two plates. Anyways, but in our syllabus, I repeat, this is just a free space. So two metal plates that are separated by an insulator forms a kind of capacitor called parallel plate capacitor. And we have parallel plate capacitor only in our syllabus. Okay, so let's discuss how each plate of a capacitor is charged. See, I keep on using each plate of a capacitor. I'm not using only capacitor. I don't say capacitor is charged in this way. No, each plate of a capacitor is charged in this way. Okay. Anyways, so this is going to be a two-way switch. Okay, two-way switch is a kind of a switch that can be turned to any of the points, point A, point B. Okay, fine. I hope you get it, how it works. See, it can go to point A like this, or it can go to point B as well, A or B like this. So this is actually called two-way switch. And yeah, this is a capacitor. Second circuit that I'm going to draw is a circuit with a load resistor. Remember here, load resistor means something that uses energy and converts this electrical energy into some other form. Simple. Here I'm just representing a resistor. Okay, it is also called load resistor. In place of this resistor, you can place a lamp, you can place a motor, you can place something, anything, an LED, a light, that's it. Okay, and this is a capacitor. Okay, this is a source of voltage and its voltage is V. Okay, remember when switch is at A, in this situation, we say that each plate of capacitor is charging. charge. Okay, how they charge? See, very simple. Previously, even I'm making this point my second point. Before each plate charges, the capacitor or each plate is neutral before we connect it to the voltage source. Okay, neutral means it had equal amount of charge. It had equal number of positive and negative charges. How I'm going to show it here? See, it was like this previously before I connected to a source of voltage. This is my capacitor. It was like this: positive, negative, positive, negative, and negative, positive, negative, positive. Okay, this was the capacitor before I connected it to the source of potential. When I connected it to source of potential, let's say this is a positive and this is a negative terminal of this source. So, the electrons will start traveling. These two electrons that you see, this one and this one, will travel from upper plate to this terminal, will transfer from upper plate of the capacitor to this terminal. On the other side, from here, the electrons will be leaving and will be going to this plate and making this plate negative charge. See, I'm going to show the charges like this: negative, 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 positive, 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 positive. This is how a capacitor is charged. I hope you understand my point. Remember one thing we studied in IGCSE, we studied in O levels as well, that only electrons transfer. Positive charges are never transferred. They do not travel. They are found deep into the nucleus, right? So only free electrons are the particles, charged particles that are transferred from one plate to the other. So what I can say that when switch is at A, so electrons from upper plate transferred to the positive terminal of the source. Okay, on the other side, electron from negative terminal transfer to lower plate of capacitor. Okay, and in this way, each plate of capacitor gets charged. I hope I'm clear to you people, right?
Yes.
Am I clear? Okay, so remember one thing, I repeat, basically only electrons are the particles that travel, okay? That's the reason why we have just described the transfer of electron when switch is connected to A. And the capacitor is storing energy, and each plate of a capacitor is getting charged. Upper plate becomes positive charge, lower plate becomes negative charge. Okay, but remember one thing. If I count, see how many charges have I drawn? See, 4 positive and 4 negative. How many charges were there altogether on the whole capacitor? 4 positive, 4 negative. Do you understand? Remember one thing: charges are conserved, or charge is conserved, you can say. Conserved during this process. Okay, remember this thing. So sometimes they ask you the question in exams: how can you show that? How can you say that charge during the storing of energy in the capacitor is conserved? So you can raise the same point. Previously, capacitor was, each plate was neutral. Okay, it means equal number of positive and negative charges. What had happened only, the the charges are only distributed. The two negative charges on the upper plate are transferred to lower plate, and two positive charges of lower plate are actually given to upper plate. They are not given to upper plate. I mean, I'm talking about the change. This is a change that takes place between the capacitor when it did not have any energy. Now it has got energy. I hope I'm clear to you people, right? Okay.
Yes,
So
sir.
this is called charging of a capacitor. Okay. Capacitor is charged in this way. Remember one thing, a very common question is asked in exams. Explain how a capacitor stores energy but does not store charge. This is a very common question, usually asked for 3 marks. Okay, so see, capacitor does not store charge. You know why? The reason is on each plate of a capacitor, charge is equal. We have mentioned we have drawn four negative charges above, four positive charges below. I'm sorry, four positive charges above and four negative charges below. Okay, so yes, so on each plate of the capacitor, charge is equal but opposite in sign. Don't you think if I sum them up, the resultant charge is zero, so does not store charge. Even this zero charge was already there before we connected it to a source. Okay, it means it was previously neutral, or as a whole, the whole capacitor was completely neutral before, and even it is neutral after. Okay, I'm not talking about each plate, I'm talking about the whole capacitor. So we explained that how or why we cannot say that capacitor is stores charge. Okay, now we have to explain that why we say that capacitor stores energy. Charges are separated, work is done to separate charges, so energy is stored. Okay, so this is a very common question. And remember, see, that's why again and again, whenever I used a word storing charge, so I've always used another word, each plate. Okay, each plate stores charge. Okay, but capacitor stores charge, wrong statement. Okay, so this is how we charge the capacitor, and this is how we can say that capacitor only stores energy but it does not store charge. Okay, I'm going to talk about a mathematical equation before I go to discharging. I think discharging will be started in the next video or next class. Okay, so we are only going to work on charging of a capacitor in this one since it's a big topic. So charging of a capacitor. So remember one thing, charging of a capacitor follows a relationship that charge stored on each plate is directly proportional to the voltage we provide to it. Okay, again I use the word charge stored on each plate. Okay, so I can say that charge, even I'm writing in words, on each plate is directly proportional to potential difference across two plates. You know,
Both the phrases are very, very important here. What two phrases I'm talking about? Charge stored on each plate. Very important, yes. And potential difference across the two plates. Very important. Anyways, so that's the reason why if I draw a graph of charge on y-axis and potential on x-axis, definitely it would be a straight line passing through origin, since direct relationship is shown in this way. Okay, so this is actually the relationship between charge and potential difference. Since we once we replace the proportionality sign with equals to sign, so we use equals to sign, okay, and we substitute a constant. Here constant is C. Okay, C is called capacitance. It is constant for each for a specific capacitor. Okay, and its definition is asked commonly. We are going to define it, but I hope you understand the relationship. Q is directly proportional to V. It is not enough to say Q only. It is charge stored on each plate. Charge stored on each plate of a capacitor is directly proportional to the potential difference across the two plates of the capacitor. Okay, and C is the capacitance here. So when they ask you the definition of C, so they ask you most of the times a statement for 2 or 3 marks. Okay, so define capacitance. Why 2 or 3 marks? Again, we need to explain every single symbol properly. We can say that the ratio gets you 1 mark. The ratio of Q upon C, Q upon V. Okay, so the ratio of charge stored on each plate to the potential difference across two plates. Okay, see, how can we get 3 marks? Number one, the correct ratio is going to get you 1 mark. Means the correct ratio means Q upon V, as we have written, charge to potential difference. Charge to potential difference. This gets you 1 mark. Second mark is obtained by using on each plate statement. And third mark is obtained by using across the two plates, potential difference across the two plates. Okay, so this is how you get 3 marks in this definition. And this is C is equal to Q over V. Q is in coulombs and V is in volts. So actual SI unit of this capacitance is coulombs per volt. But since a scientist wanted to take the credit and his name was Farad, so he named this unit as Farad. Okay, represented by capital F. Farad is a very, very big unit, so that's the reason why we will only be dealing with microfarad once we'll go for calculations. Okay. Anyways, so SI unit of capacitance is Farad. Okay, and sometimes they ask you the definition of Farad as well. Okay, so define Farad. I always told you a number of times that when we define physical quantity, so we define it by using physical quantities, and when we define the unit, so we actually define it by using units. So Farad is the SI unit of C, capacitance. If we know the equation of C, V upon Q upon V, we can easily define Farad. So Farad is a SI unit of capacitance, and Q has a unit of C, V has a unit of V. This is Farad. Okay, so we can say that the ratio of coulombs to volt is called farad. That's very simple. You can add one more sentence into it. It is the SI unit of capacitance. But if they ask you define farad and you only write this statement, it is the SI unit of farad, it is the SI unit of capacitance, you are not going to get the marks on it. Okay. So this is how we define farad. And I told you farad is a very large unit for capacitance. We will be dealing with microfarads most of the times. I hope you get it right.
Yeah.
Okay, fine. Calculations will be done later on, but let's do one more thing. The graph that we discussed here. Okay, this graph has a few features that are going to be very useful for us. Okay, and the features are number one, it's gradient. Okay, so the gradient of this graph is C. We have an equation for gradient, change in y upon change in x. Change in y is q, change in x is v. Okay, so don't you think q upon v is capacitance, right? That we have described above as well. We can say that the graph of this, gradient of this graph is always equal to the capacitance. So if you want to calculate the capacitance, you just calculate the gradient, will get you the capacitance. But remember one thing, it should be a straight line, okay? Anyways, second thing is area under graph. Remember, area under graph of in this graph is equal to, by the way, if I calculate area under graph by using a triangle, see, so area under graph is half base into height, Q into V or V into Q. This is always equal to energy stored on the capacitor. Okay, we can show it as well. We can prove it. Okay, even I'll ask you people to prove it. That energy is area under the QV graph. Okay, there is another formula of energy. Okay, I'm just writing it simply, half Q into V is equal to energy. You just imagine if you substitute Q equals CV, so the equation becomes half in place of QV. If you substitute, sorry, in place of Q, you substitute CV, it becomes CV square. Okay, this is another equation of energy, calculating energy. What if you substitute V as Q upon C? So in the same equation, another equation becomes E equals half of, you are substituting in place of V, Q upon C, so Q square upon C. You know these two equations, equation 1, 2, 3, this equation 2, and this equation 3 derive two more relationships. How? I'm going to explain. C, this is constant, half in C. Here, this is constant, half in C. Okay, so we can clearly see that from relationship number 2, energy is directly proportional to square of V. Yes, this is a relationship, and by this, you can make an equation that we used to do. E1 upon V1 square is equal to E2 upon V2 square. Very useful equation. In some questions, when they ask you energy of a capacitor was this much when voltage was this much, okay, what will be the energy if voltage is doubled or this much? So you will be using this equation directly, okay, and can easily solve it. On the other side, for the other one, for this one, you know, energy is directly proportional to square of charge as well. So you can say that energy square of charge E1 upon Q1 square is equal to E2 upon Q2 square. Okay, this is another equation. So I repeat, energy is area under graph. Energy is equal to half Q into V. Energy equals half CV square. Energy equals half Q square upon C. Okay, these are the three equations. And from the last two equations, we derived two more relationship. Why couldn't we derive one relationship from equation one as well? Since in equation one, nothing was constant other than 1/2. That's it. Okay, that's the reason why we cannot make a relationship or proportionality of two things. Okay, that's why I would say, equation number two and equation number three are more useful in this situation. Okay, I hope you get it right.
Yes.
Okay, fine. So I repeat quickly, capacitor, a component that stores energy. Capacitor stores charge on each plate. How? I told you the resultant charge on each capacitor, I mean on capacitor, is always zero, and charge always conserves. Okay, we studied it. We studied why we can say that capacitor stores energy, but it does not store charge. We explained it. We actually saw a graph. Okay, QV graph. It's a straight line passing through origin. The reason is the capacitor has a relationship. Q is directly proportional to V. Okay, capacitance, yes, is the ratio of charge stored on each plate of a capacitor to the potential difference across the plates of the capacitor. Okay, so this is the common, relationship, and yeah, we can define Farad. We defined it, and we actually derived three relationships of energy. Okay, I hope you get it right. I want you people to derive E is equal to half of Q into V. Okay, for this, I'm giving you people 2 minutes and your time start. See, if we start with the basic equation of potential difference, what is potential difference equals to energy upon charge, right?
Yes.
And energy will be equal to VQ, right? But why half? The problem is, I told you even in AS level as well, that if we have a quantity that is not constant, that is increasing continuously. Okay, for example, charge is continuously increasing, right? So Q and V, and it is increasing linearly. Okay, so if it is increasing linearly, so in that case, you can take an average of that. Okay, so you just imagine charge has two values. One of the values is 0, the other value is Q, let's say. Okay, so I'm taking an average of 0 and Q. Okay, so what do you think? The average of 0 and Q would be Q plus 0 upon 2, isn't it? The two values, the sum of two values divided by 2. Eventually, what happens here? E equals half of Q into V. I hope you get it right.
Yes.
That's the reason why
ट्रायंगल की
the
फॉर्म में इसलिए पढ़ सकते हैं हाफ बेस इनटू हाइट
नहीं नहीं देखो, वो तो आपने ट्रायंगल का फॉर्मूला, आई अंडरस्टैंड यू फाउंड द फॉर्मूला. Basically, this thing is secondary thing. We first derive the equation. Forget that the energy stored on in a capacitor is equal to area under the graph. Forget it. Okay, suppose I directly give you this equation derived. Okay, how would you derive it? You would derive it like this. Yes, after you derive it, you got to know, okay, fine. It looks like, it is area under the graph. That's another case. It is area under the graph. Area under the graph, being area under the graph is actually not the primary thing. It is not the basic thing where we start from. We should start from some basic equation. And basic equation is potential difference is equals to energy upon charge. I hope you get it right. And charge, since charge is increasing linearly, something that increases it linearly, you have to take its average. Okay, so you better write here average charge. Okay. And once you take an average, so average is first value of charge, that is 0, plus second value of charge, that is Q, divided by 2. This is how you derive the equation. Okay. Fine. So